Okay students, so let us continue. So in the previous class we discussed how diborane can be prepared. So that is done. Now let us discuss the structure of diborane. Diborane has an interesting structure because now here it's just different from our normal structures that we have seen, because diborane, the molecular formula is B2H6. That means two boron is there and six hydrogen. So two hydrogen, it is observed that it's a normal terminal BH bond. You will see it is normal two center two electron bond. What do you mean by two center two electron bond? Look at this. This BH bond, how it's formed? One electron coming from this boron and one electron coming from this hydrogen. So that's the way we normally have seen, right? So this is a normal covalent bond formed between this boron and this hydrogen. Similarly, this. So this is actually a two center two electron bond. That's what we will say. Now, still two more hydrogen is there. That hydrogen actually now forms a bridge-like structure in which now this if this BH bond, if you draw like this, that means this BH bond, that is bridge bond, actually not is in the plane. It is, you can draw like this should not be in the same plane. So this BH is coming above the plane, and this BH you can imagine that's coming below the plane, like that. So this is a special type of bond that you have seen in diborane. This bond we will call banana bond, because now here what's the speciality? We know the electronic configuration of boron. It is 1s2 2s2 2p1. That means 3 electron is available for boron. Look at here, already one is bonded here, one is bonded here. Now one more electron is there. With that one electron, actually these two BH bridge bonds are formed. That suggests it's a not a normal bond that we will see. Here 1, 2, 3. 3 center and available 2 electron. One electron is definitely coming from hydrogen, and with this one boron have one more electron, so any one of them will be bonded. So what that means, we will say diboron is an electron deficient compound, and this bridge bond we will call 3 center 2 electron bond, because available 2 electron, these 3 atoms, this BHB bridge bond are formed. So that makes a special bond that we will call banana bond. So let us note the angle. This bond angle is 97 degree, and this terminal BH bond is 120 degree. And the bond length definitely will be different. This is 134 picometer, and the terminal BH bond will be 119 picometer. So this is the way the bond length is different, and now bond strength is also different, because in the bridge bond there is no sufficient electron is available. That why most of the boron compounds we will say it's an electron deficient compound, so they can act as a Lewis acid because they can accept lone pair of electrons. So this is the basic structure of diborane. And if you talk about the hybridization, we can think boron having a configuration like this. Boron in the excited stage, it will become 2s2 1s2 2s1 2p2 configuration, 2s1 2p2 configuration. So but now this actually undergoing a sp3 hybridization. So sp3 hybridization means 4 hybrid orbitals. So 2 hybrid orbital is used here, 2 is used here. The speciality is one hybrid orbital do not have an electron, while other 3 hybrid orbital having an electron. So that's how the hybridization is. Diborane, each boron atom undergoing sp3 hybridization. So this is what now you can understand about the structure of diborane. Now let us now discuss the uses. Diborane has very important uses that you can always remember, because Diborane is such an important compound that used for the preparation of primary alcohol from carboxylic acid. So that means it's a very good reducing agent. We know lithium aluminum hydride is a very powerful reducing agent. Like that, diborane is equally powerful that it has the ability to reduce carboxylic acid into primary alcohol. So that's first important use that you can remember. Diborane used as a reducing agent in our organic reaction. Reducing agents. Then second important use, yes, is used for the preparation of borohydrides like lithium borohydride and sodium borohydride are prepared now using diborane. So that is the another use of diborane that you can remember. Okay, which is again lithium borohydride and sodium borohydride. Again, now they are good reducing agents. They are good reducing agents. NaBH4, sorry. Lithium borohydride, sodium borohydride. These are good reducing agent. Then used as a catalyst in polymerization reaction. That's another use. It can act as a catalyst in polymerization reaction. Next important use that we can remember that act as a rubber vulcanizer. Rubber vulcanizer. We already know the vulcanization of rubber actually increases the strength. So now sulfur crosslinking is made for that. Now it can act as a supporting role for the vulcanization process, which actually increases the strength of rubber. Next, used in rocket propellants. Used in rocket propellants. Used in rocket propellants. Next is used as a doping agent for the production of semiconductor. Doping agents for the production of semiconductor. We know semiconductors have so many applications, used in transistors, diodes, etc. So these, semiconductors were, when it's doped with this 13th group elements and 15th group elements, is actually increases its conductivity. So that why boron is coming in the 13th group elements. So the doping will be like p-type semiconductor. So it's actually acting. Diborane can act as a doping agent and as well as used as an intermediate in the production of pure boron for the semiconductor purpose, for the preparation of pure boron for the semiconductor purpose. So these are the important uses of diborane. Any three important that you can remember. Okay, so that's all about one of the important compound, that is diborane. Next we can discuss Borazine. What is Borazine is all about? The first point you can remember about Borazine, it's called popularly called inorganic benzene. It's called inorganic benzene. Why it's so? You will understand if you look at the structure. Boron, nitrogen, boron. You can see alternating boron and nitrogen bond and alternating single and double bond. So that is now very much similar to benzene, where now benzene we draw like this. So what's the basic difference? Here now in benzene every atom is carbon and now hydrogen atom definitely there. In this Borazine, here you will see, yes, here you will see boron nitrogen. Boron and nitrogen are in the alternating position in the ring system, and you can see hydrogen atom attached to the each ring atoms, and look at the number of electron around a particular atom. Here this carbon atom actually have a valency 4, so the one bond actually made up of 2 electrons, so total 8 electron will be there in each atom. Similarly here also you can see it is not 8 electrons, so these two are isoelectronic. If you compare with the benzene, these two are isoelectronic and isostructural with the benzene. That's why you will call this Borazine as an inorganic benzene, because it's very much similar to benzene, but here instead of carbon you will see boron and nitrogen atoms are present. So alternative single and double bond also you will see, but the main difference is here these pi electrons are perfectly delocalized, so we can say this is a perfect aromatic compound, while this is boron nitrogen bond. You can understand nitrogen is more electronegative, so boron nitrogen bond is actually polar, and actually one more nitrogen hydrogen bond is also polar. That means delocalization of electron is not that much. We can say in Borazine only partial delocalization takes place, while in benzene there is a complete delocalization. That means this is benzene is a perfect aromatic compound, while this is not that much a highly aromatic compound, because these are more polarity is there among the bond, while here carbon carbon bond and carbon hydrogen bonds are both are non-polar in nature. That's why difference is there, but the physical properties very much similar to both, but chemical properties you will see a difference, mainly because of the difference in aromatic behavior. So first let us discuss the preparation, how you can prepare Borazine. First important method, yes, treated with lithium borohydride and ammonium chloride. So lithium borohydride. Lithium borohydride is treated with ammonium chloride. Lithium borohydride, when treated with ammonium chloride, you are actually getting at a temperature of 230 degrees Celsius. 230 degrees Celsius. Borazine will be formed B3N3H6. B3N3H6. That's Borazine for you. Along with that, lithium chloride and hydrogen gas will be released. Lithium chloride and hydrogen gas will be released. Lithium chloride 3 moles and 9 moles of hydrogen gas. So this is the method of one of the method of preparation of diborane, by treating lithium borohydride with ammonium chloride at a high temperature of 230 degrees Celsius. Next is now treating with ammonia, that is diborane, when it's treated with ammonia in a ratio of 1:2, that is 3 moles and 6 moles of ammonia. When it's treated at a temperature, higher temperature 300 degrees Celsius, you will see Borazine again, it's forming. So this is the most important method of preparation, because that's related to diborane as well. So you can learn that it's a reaction of diborane or at preparation of Borazine. So diborane, when it's treated with ammonia in a 1:2 molar ratio, you're actually getting at a higher temperature Borazine will be obtained. Talk about physical properties. Yes, it's just like a liquid like benzene. So it's now liquid at room temperature, existing as a liquid with a boiling point of 63 degrees Celsius. So now it has that volatile nature, and next you can remember reactivity. Benzene is less reactive because of the more stability by delocalization of electron takes place, which makes it's a perfect aromatic compound. So benzene will be more stable, while Borazine no is not that much stable. It's not no. It's more reactive than benzene and thermally less stable as well. So chemical properties are really different from benzene, but no, some of the physical properties are very much closer. And we saw the isostructural and isoelectronic with the benzene. So let us discuss one by one. Talk about thermal stability. No, it's not that much stable. Thermal stability. When Borazine heated to a higher temperature, you will see diborane and hydrogen will be formed. So that is the first point you can remember. Borazine on decomposition it will give hydrogen and other some extra compounds are also forming B3N3H6 when it's not heated to higher temperature. First is diborane also forming, hydrogen is also forming, plus some other volatile compounds. So that's the way it decomposes at a higher temperature to yield diborane and hydrogen and other some volatile compounds. Action with HCl, yes, it do react with HCl. While now you will not see benzene it not easily decomposes or it react with HCl. Both is not there in the case of benzene, but diborane do react. Diborane react with HCl to form a product B3N3H9Cl3. So what's happening here? Here now already I drawn the structure, right? So Borazine in which boron. If you compare boron nitrogen bond, nitrogen is more electronegative. So partial negative charge will be there on nitrogen, partial positive charge will be there on boron. So the addition will take place in such a manner. Hydrogen is partially positive and chlorine is partially negative. So this negative part actually joined with the positive part of Borazine, that's boron. So boron chlorine bonds actually forming and nitrogen and hydrogen bonds will be formed. So pi bond will be broken and you will see B3N3H9Cl3 will be formed. And this on decomposition at high temperature around 100 degrees Celsius, if you decompose it, you will get B3N3 at B3N3 H3Cl3 plus hydrogen gas actually emitting. That means here you will see uh, trichloroborazine is forming. Trichloroborazine is forming. So remember this is the chlorine is attached with the bromine. So sorry, chlorine is attached to the boron. So that why we will write like this B trichloroborazine. So that is a structure that forms when this compound when it's heated strongly you will get trichloroborazine. Now talk about reaction with the water. Yes, again this is only for Borazine. It's not given by this benzene. So Borazine do react with the water. First you will see water I written like HOH where OH the negative part actually joined with the boron and it's joined with the nitrogen. First an attack will be formed. These two are combined to give a product like this boron hydrogen OH NH2 thrice. So you can represent like this, an attack will be formed where OH actually joined with the boron and hydrogen joined with the nitrogen. So like that a structure will be formed first. Then you will see at a higher temperature, this when heated at a higher temperature around 100 degrees Celsius, yes. This time the 9 molar ratio, 9 moles of water, higher molar ratio, you will see this boric acid will be formed. H3BO3. That's another important boron compound that we will discuss later. That's boric acid, and ammonia and hydrogen will be formed. So that shows that Borazine actually undergo hydrolysis reaction. Now action with the bromine. Yes, it's do react with the bromine as well. So we can write like this. 3 moles of bromine. Here you will see now bromine undergo heterolytic cleavage. That means Br plus and Br minus will be there. So both no every atom boron and nitrogen bromine will be added. So you getting a structure B3N3 at 6 Br6. So bromine will be there at now both boron and nitrogen. This compound on heating at high temperature 60 degrees Celsius you will see B3N3 at 6, sorry, B3N3 at 3 Br plus HBr will be eliminated. So now that's you will see elimination of hydrogen bromide will take place when now this particular compound heated at high temperature around 60 degrees Celsius. So that is the action of diborane with the bromine. Now let us know, we already discussed the structure. Now if you talk about bond length of boron nitrogen in Borazine is actually coming around 144 picometer, where which is very much similar to carbon-carbon bond in benzene. It is actually 142 picometer. That again suggests the kind of similarity with the benzene. And hybridization again, each boron and nitrogen undergo sp2 hybridization, similar like borazine, similar like benzene, where each carbon atom undergo sp2 hybridization, where they having a planar structure where pi bond will be above and below to the plane. Like that, borazine also the pi bond will be present above and below the plane. So similarities is there, but it's not like our normal benzene. One important difference you will see in the structure where boron having 3 electron in the valence orbital and nitrogen having 5 electron. So one boron nitrogen bond is actually a pi bond. A pi bond is formed. That is actually a 2 electron is contributed from nitrogen itself. So lone pair of electron is also utilized. So that how that fourth bond actually is formed, which suggests that will be a coordinate bond which is contributor from nitrogen. So boron having 3 electron, nitrogen having 5 electron, 5 plus 3 8. That how the 8 electron is utilized by these two atoms. So that's we will see the structure of diborane, and like benzene, this also having a resonating structure. So pi electrons are delocalizing, not perfectly like benzene, that's all. So these are the resonating structure and resonance hybrid. You can draw like this, like now we do in benzene. So that's all about this Borazine and its structure and its uses. Now two uses that we are saying, one is used as a precursor to grow boron nitrate thin films on the surface of metals like rhodium. So it actually acting as a precursor, that means prevent the formation of this boron nitride on the surface of metals like rhodium. Then it has other uses like used in neutron detection and gasoline additives, and a catalyst for polymerization of alkene, used as fire retardants in cottons and nylon textiles, and polymerization inhibitor of unsaturated alcohols and esters, and starting material for the potential ceramics such as boron carbonitrides. So any three important that you can use as a fire retardant, you can remember, and catalyst for the polymerization of alkene, you can remember, like that. No, any three you can remember. Okay, so that all about Borazine for you. Okay, so let us wind up now. Thank you.